In recent years, AI techniques for game playing have achieved remarkable results. For example, in 2017, the Libratus AI defeated 4 top human specialist professionals in heads-up no-limit Texas Hold'em poker. These results show that it is possible to compute strong solutions to two-player zero-sum games in theory and practice. This is not the case for games with more than 2 players, which remain one of the main open challenges in computational game theory. Many strategic interactions provide players with incentives to coordinate and share their final reward. In this paper, we are interested in ex-ante-coordination, where the team members have an opportunity to discuss and agree on tactics before the game starts, but will be unable to communicate during the game, except through their publicly observed actions. This is the case in a poker game with 3 or more players, where all but one of them collude against a target player and will share the winnings. In other settings, players might be forced to cooperate by the nature of the interaction itself. This is the case, for instance, in the card-playing phase of bridge. Team games can be used to model non-recreational settings as well, such as war, where the colluders do not have time or means of communicating during battle, collusion in bidding, where communication during the auction is illegal, and so on. Ex-ante-coordination can enable the team members to obtain significantly higher utility than they would obtain by abstaining from coordination. Unfortunately, finding an equilibrium with ex-ante-coordination is hard and inapproximable. A team that ex-ante-coordinates can be modeled as a single meta-player with imperfect recall. Then, solving the game amounts to computing a Nash equilibrium in normal form strategies in a 2-player, zero-sum, imperfect recall game. The focus on normal form strategies is crucial. Indeed, while behavioral strategies provide a compact representation of the player's strategies, they cannot be employed in imperfect recall games without incurring a loss of expressiveness. Our first contribution is a new game representation which we call the realization form. This representation is useful because it enables one to represent the strategy space of a player as a polytope in a low-dimensional space. This holds even in games with imperfect recall. The price to pay is the complexity of the polytope that in imperfect recall games might be described by an exponential number of constraints. Our second contribution is the auxiliary game. It provides a sound way to map the problem of finding an optimal ex-ante-coordinated strategy for the team to finding a Nash equilibrium in a 2-player zero-sum game with perfect recall. By reasoning over the auxiliary game, we propose an anytime algorithm called fictitious team play that is guaranteed to converge to an optimal solution in the setting where the team members coordinate ex-ante. Experiments show that it is dramatically faster than the prior state-of-the-art algorithms for this problem.